Karibuni katika mfululizo wa vipindi vyetu vya YouTube. Naitwa Samachibia na leo tunaenda kuangalia carbohydrates. By definition, carbohydrates are the compounds which contain carbon, hydrogen and oxygen. And the ratio between hydrogen and oxygen is 2:1. So there are so many compounds which contain carbon, hydrogen and oxygen, but the unique property to carbohydrate which distinguishes it from other compounds which contain these elements is the ratio between hydrogen and the oxygen, which is 2:1. They are known as hydrates of carbon, carbohydrates. Hydrates of carbon, which means that they are obtained by adding water to carbon atoms. As we shall see the general formula of carbohydrates. For example, in hexose, the carbohydrates which contain 6 carbon atoms, the ratio between hydrogen and oxygen is 12:6, which is 2:1. Also, in thioses, which contain 3 carbon atoms, the ratio between hydrogen and oxygen is 6:3, which is equal to 2:1. Similarly, in carbohydrates which contain 5 carbon atoms, such as ribose, the ratio between hydrogen and oxygen is 10:5, which is still 2:1. However, not all carbohydrates contain hydrogen and oxygen in this ratio. There are some carbohydrates which do not have this ratio. One example of this is deoxyribose. Deoxyribose contains 5 carbon atoms. It has 5 carbon atoms, 10 hydrogen atoms, and 4 oxygen atoms. The ratio between hydrogen and oxygen in this compound is not 2:1, as you can see. 10:4 is not equal to 2:1. So we say the term carbohydrate is not exact term, but it is a convenient term because not all carbohydrates obey this general formula or the ratio between hydrogen and oxygen. There are so many basic properties of carbohydrates which distinguish carbohydrates from other classes of organic compounds. The 3 basic properties are the ratio between hydrogen and oxygen atom is 2:1 in all carbohydrates except few, such as deoxyribose. Another basic property is the functional group which they contain. All carbohydrates are aldehydes or ketones, which means that they contain an aldehyde group or a keto group. We shall see examples of aldoses and examples of ketoses. Another basic property of carbohydrate is that they contain several hydroxyl groups. In carbohydrates, every carbon atom except the one which carries the functional group have one hydroxyl group. So they have several hydroxyl groups. For example, glucose has 6 carbon atoms. About 5 carbon atoms contain one hydroxyl group per each carbon. And the one which contains the functional group, it does not contain the hydroxyl group, but 5 carbon atoms contain hydroxyl groups. In carbohydrates with 5 carbon atoms, 4 carbon atoms contain hydroxyl groups, except the one which is an aldehyde of ketone. Anyway, we have discussed a little bit about the definition of carbohydrates, the general formula of carbohydrates. The general formula of carbohydrate is carbon X, then water Y. Okay, let us discuss about classification of carbohydrates. There are 3 main classes of carbohydrates, which are monosaccharides, disaccharides, and polysaccharides. But before obtaining these 3 classes, we first classify carbohydrates into 2 classes, which are sugar and polysaccharides. So there are mainly 2 classes of carbohydrates, which are sugar and polysaccharides. Sugars can be also classified into 2 main groups, depending on the number of sugar units, monosaccharides and disaccharides. So generally, if you are asked to list the 2 classes of carbohydrates, you are supposed to say we have sugar and polysaccharides. If you have been asked to mention the 3 classes of carbohydrates, we have monosaccharides, di, and polysaccharides. So this is classification of carbohydrates. We shall look about the properties of sugar and polysaccharides, and then we shall discuss a little bit about the properties of monosaccharides, disaccharides, and polysaccharides with the examples and general structure of each group. Okay, monosaccharides are the single sugar units. These are carbohydrates which cannot be hydrolyzed to yield any product. Their properties are so many, including the following. All monosaccharides have sweet taste. They are single sugar units, as we said. They are all soluble in water. They are crystalline. Their names always end with a suffix "-os", for example, glucose, galactose, fructose. They are all reducing sugars. There is no N monosaccharide which is non-reducing. Their general formula is this one: carbon, hydrogen to oxygen, and then this is the number of carbon atoms. So N is the number of carbon atoms in this formula. The number of carbon atoms in the monosaccharides always starts from 3 to 9. The classification of monosaccharides is basically on their number of carbon atoms. There is also classification according to their functional group, as we shall discuss later. But let us start with the classification of monosaccharides according to their number of carbon atoms. As we said, the number of carbon atoms start from 3 to 9. Monosaccharides which contain 3 carbon atoms are known as trioses. Examples of this are glyceroldehyde and dihydroxyacetone. So these are regarded as the simplest carbohydrates or the simplest monosaccharides, since there is no N other carbohydrate which has the number of carbon atoms less than 3. So if you are asked to mention the simplest carbohydrates or the simplest monosaccharides, your examples are trioses. Trioses perform many functions, but the major function of trioses is that they are intermediates in the glycolysis of aerobic respiration or anaerobic respiration and the dark reaction or the light independent stage or reaction of photosynthesis. So that is the function of triose. Tetrose are the monosaccharides which contain the 4 carbon atoms. So we expect their molecular formula or their general formula to be carbon 4, hydrogen 8, and oxygen 4, according to the general rule of monosaccharides of carbohydrates, that the ratio between hydrogen and oxygen should remain 2:1. There are so many examples of pentose, but the most common ones are ribose, deoxyribose, ribose, arabinose, and thyrose. Functions of pentose. There are so many functions of pentose, including the following. First of all is formation of nucleic acids. For example, RNA is made up of ribose. Also, DNA is made up of deoxyribose. Another function is the synthesis of ATP, which requires ribose. Ribose biphosphate is made from a 5-carbon sugar, which is ribose, and it is used in carbon dioxide fixation in plants. Hexose are the 6-carbon sugars, so N is 6 in these compounds. For example, glucose. We have galactose, fructose, mannose, and sucrose. So there are so many examples of hexose, including this. Functions of hexose are they are sources of energy when oxidized. For example, glucose is commonly used in respiration. Another function is the synthesis of disaccharides. For example, glucose plus glucose, we get maltose. Another example is the formation of sucrose, which requires glucose and fructose. Another example is the formation of lactose, which requires glucose and galactose. Another function of hexose is the synthesis of polysaccharides. For example, many alpha-glucose forms starch and glycogen. Also, many beta-glucose forms cellulose. Structure of trials. So let us discuss about the structure of trials. As we said, there are mainly two examples of trials: glycerolaldehyde and dihydroxyacetone. Let us start with the structure of glycerolaldehyde. First of all, you are supposed to know the functional group of glycerolaldehyde. The functional group of this compound is an aldehyde group. As we said, it is positioned at the carbon atom number 1. This is the carbon atom number 1. And this is the functional group, glycerolaldehyde. So it is an aldehyde group. It is the carbon atom which is bonded to oxygen atom, and then it has been bonded to hydrogen atom only on one side. So the aldehyde group always is positioned at the carbon atom number 1, or at the end of the compound. So the carbon number 2 and carbon number 3 contain hydroxyl groups, as we said. And the position of hydroxyl groups is on this side. So carbon number 2 is this one, and carbon number 3 is this one. So this is the first carbon atom, the second carbon atom, the third carbon atom. So this is glycerolaldehyde. You are supposed to know how to draw this diagram and to indicate the location of the functional group. Okay, dihydroxyacetone. This name dihydroxy suggests that this compound is a keto group, has a keto group and not an aldehyde group. And then dihydroxy means it has two hydroxy groups. So the first hydroxy group is this one, the second hydroxy group is this one. So keto group is positioned at carbon atom number 2 and not carbon atom number 1. So this is the keto group, this one. It is the carbon atom which has directly bonded to oxygen atom by double bonds, and then it has been bonded to carbon atoms on both sides. So this is the first carbon atom, this is the second carbon atom, and this is the third carbon atom. So you are supposed to know the functional group of dihydroxyacetone, which is the keto group, before you draw it. Let us turn to pentose. The first pentose which we are going to discuss is ribose. Ribose has 5 carbon atoms and it has an aldehyde group. As we know, the aldehyde group is always positioned at carbon atom number 1. So this is an aldehyde group. It is the carbon atom which has double bond with oxygen, and then this carbon which is bonded to oxygen by double bond is also bonded to hydrogen only at one side, and then on another side it is bonded with carbon. So this is an aldehyde group. So the first carbon atom is this one, the second carbon atom is this one, and this is the third carbon atom, fourth and fifth carbon atom. So carbon atom number 2, number 3, number 4, and number 5 all contain hydroxyl groups. The position of these hydroxyl groups determines the structure of the compound when it forms the ring. If all hydroxyl groups are positioned in this side, means that when the ring is formed, no any hydroxyl groups should be projected into the ring. Any hydroxyl group which is positioned in this side should be projected into the ring. So the open structure of ribose suggests that in its ring structure there is no any hydroxyl group which is projected into the ring. So into the ring we are expecting to find only hydrogen atoms. In forming the ring structure, the carbon atom number 1 and the carbon atom number 5 forms the bond. In carbon atom number 1, we have this double bond, so there is sigma bond and pi bond. The pi bond is broken, and oxygen atoms in this bond, electrons in this bond are moved into oxygen. So oxygen becomes negatively charged and the carbon becomes positively charged. So carbon atom number 1 becomes positively charged and the oxygen of carbon atom number 1 becomes negatively charged. Also, in carbon atom number 5, there is this bond between oxygen and hydrogen atoms. It is this bond which is broken during the formation of the ring structure. So, oxygen being the most electronegative atom and hydrogen, it takes all electrons and it becomes negatively charged, while hydrogen becomes positively charged. In forming the ring structure, the negatively charged oxygen of carbon number 1 forms the bond with the positively charged. The negatively charged oxygen of carbon number 1 forms the bond with the positively charged carbon number 5. So, this is oxygen atom, which was previously negatively charged. So, this is oxygen atom of carbon number 4. This one. Carbon number 4 is this one, and the oxygen which was negatively charged is this one. It forms a bond with a positively charged carbon atom number 1. So this is oxygen of carbon atom number 4, and this is carbon atom number 1, which is positively charged. So this is carbon number 4, this is the oxygen of carbon number 4, and this is carbon number 1, carbon number 2, carbon number 3. So this is a 5-membered ring, which means that it has 5 members. The first member of the ring is oxygen of carbon number 4. The second member of the ring is carbon atom number 1. The second member is carbon atom number 2. Third member is carbon atom number 3. The fourth member is carbon atom number 4. So we have the first member, the second member, the first member, the second member, the first member, the second member, third member, fourth member, and fifth member. So it is a 5-membered ring. One carbon atom projects out of the ring. It is not the part of the ring. This is carbon atom number 5. So it has 2 hydrogen atoms and it has 1 hydroxyl group, as you can appreciate from this formula. So from this structure, ribose forms the 2 isomers in its ring structure, which are alpha ribose and beta ribose. The difference between alpha ribose and beta ribose is the orientation of hydroxyl groups, especially at carbon atom number 1. In alpha glucose, the hydroxyl group at carbon atom number 1 projects down in the ring, this one. While in beta ribose, the hydroxyl group at carbon number 1 projects upward. Arrangement or orientation of hydroxyl groups in other carbon atoms do not differ. As you can see, all hydroxyl groups project out of the ring. So there is no any hydroxyl group into the ring. Remember this structure. So this is alpha ribose and this is beta ribose. Structure of deoxyribose. The only difference between ribose and deoxyribose is that deoxyribose has only 4 oxygen atoms and not 5 oxygen atoms. So in deoxyribose, at carbon number 2, there is no oxygen. This is an open structure of deoxyribose. As you can appreciate, this is the aldehyde group. And there is no any hydroxyl group which is positioned in this side. So we do not expect to find any hydroxyl group inside the ring. As we discussed for ribose, the only difference between ribose and deoxyribose is carbon atom number 2. At carbon atom number 2, there is no any hydroxyl group in deoxyribose. While in ribose we saw there was an hydroxyl group which was projected outward the ring, or there is no any oxygen atom at carbon number 2 of the deoxyribose. So this is carbon number 1, carbon number 2, carbon number 3, carbon number 4. And the oxygen of carbon number 4 is this one, and it has become the part of the ring. So we say this ring is 5-membered. The first member is the oxygen of carbon number 4. The second member is carbon number 1. Third member is carbon number 2. Fourth member is carbon number 3, and fifth member is carbon number 4. So this is carbon number 1, carbon number 2, number 3, carbon number 4. Carbon number 5 is out of the ring, as you can see it here. The only difference between alpha deoxyribose and the beta deoxyribose is the orientation of hydroxyl group at carbon number 1. In alpha deoxyribose, the hydroxyl group is projected downward. This one is projected downward. While in beta deoxyribose, the hydroxyl group is positioned outward. This one. So the only difference is the position of hydroxyl group at carbon number 1. If it is projected downward, and then this isomer is alpha isomer or alpha deoxyribose. If it is projected outward, this one, it is beta deoxyribose. So another structure is that of hexose. We have so many examples of hexose, but let us start our discussion with the structure of glucose. Glucose is an aldose. This means that it has an aldehyde group at carbon number 1. It has 6 carbon atoms, 1, 2, 3, 4, 5, 6. Orientation of hydroxyl group is the one which determines the ring structure of glucose. The hydroxyl group at carbon number 3, this one, is oriented in this side, while the other hydroxyl groups are oriented to this side. So what you are supposed to be careful is the orientation of hydroxyl group in carbon number 3. For all glucose, I mean alpha and beta glucose, it must be oriented in this side, while the other hydroxyl groups should be in this side. So the hydroxyl group in carbon number 2 is this one. If you put it in this side, means you are wrong. Hydroxyl group in carbon number 3 is in this side. If you put it in this side, you are wrong. Hydroxyl group in carbon number 4 is in this side. If you put it in this side, you are wrong. Similarly, in carbon atom number 5 and number 6, they are oriented in this side. And implication of this is that if hydroxyl group is oriented in this side, it should project into the ring. So let us discuss about the formation of the ring in a glucose. Glucose have 2 ring structures, which are alpha glucose or alpha isomer and beta glucose or beta isomer. In formation of the ring, the bond between oxygen and carbon number 1 breaks in such a way that all the 2 electrons from this pi bond goes to oxygen. So carbon is left with positive charge and oxygen becomes negative charge. Another bond breakage occurs at the OH group of carbon number 5. This one. Oxygen, being the more electronegative atom, takes all the 2 electrons from this bond and it becomes negatively charged, while hydrogen becomes positively charged. So we have the positively charged carbon atom number 1 and a negatively charged oxygen atom of carbon number 4, of carbon number 5. This is carbon number 5. The oxygen, which is negatively charged, bonds with the hydrogen, which is positively charged, leads to the formation of OH at the carbon number 1, this one. And the positively charged carbon number 1 bonds to the negatively charged carbon number 5. So this becomes a ring structure due to the combination between the carbon number 1 and oxygen of carbon number 5. So this is carbon number 5, and the oxygen of carbon number 5 is this one. Or carbon number 5 is this one, its oxygen is this one. So carbon number 5, its oxygen is this one. Because it is negatively charged, it bonds to carbon number 1. So this is oxygen of carbon number 5, and this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. So the ring structure in a glucose is 6 membered, which means that the ring is formed by 6 members. The first member is the oxygen of carbon number 5. The second member is carbon number 1. Third member is carbon number 3. Carbon number 2. The fourth member is carbon number 3. And the fifth member is carbon number 4. And the sixth member is carbon number 5. So the ring is a 6-membered ring. Carbon number 6 is out of the ring, and it contains 2 hydrogen atoms and 1 hydroxyl group. So this is for alpha glucose. Alpha glucose differs from beta glucose in their orientation of hydroxyl groups at carbon number 1. In alpha glucose, the hydroxyl group is projected downward, while in beta glucose, the hydroxyl group at carbon number 1 is projected outward. Orientation of hydroxyl groups and hydrogen atoms in other carbon atoms do not differ between alpha and beta glucose. So what you are supposed to know is that in the ring structure of either alpha or beta glucose, hydroxyl group at carbon number 3 should be projected into the ring. This one should be projected into the ring. And then in alpha glucose, hydroxyl group at carbon number 1 down the ring, at carbon number 1 in beta glucose upward the ring. Structure of galactose. The structure of galactose is similar to that of glucose, except the orientation of hydroxyl group at carbon number 4 is projected out is in this side and not in this side. Orientation of hydroxyl group and hydrogen atoms is similar in all other carbons as that of hydrogen, as that of glucose. In the ring structure, in forming the ring structure, the carbon atom number 1 forms the positive charge due to the bond linkage between the carbon and the oxygen, while the OH group of carbon number 5 forms the positive charge in hydrogen and the negative charge in oxygen. So the positively charged carbon atom number 1 forms the bond with the negatively charged oxygen group of carbon atom number 5. So the result is the 6-membered ring is the one which has been observed in glucose. So you can appreciate the difference between galactose and glucose in the carbon atom number 4. In alpha and beta glucose, hydroxyl group is projected downward, but in the galactose, it is outward. So this one is the only difference between the galactose and the glucose. In all forms of galactose, which are alpha and beta galactose, the hydroxyl group at carbon number 4 should be outward. The difference between alpha galactose and the beta galactose is that in alpha galactose, the hydroxyl group at carbon atom number 1 is down the ring. While in beta galactose, the hydroxyl group at carbon atom number 1 is outward the ring. So other orientations remains similar. Fructose is a keto sugar. It contains a keto group at carbon atom number 2. This is the keto group. So carbon atom number 1, number 2, 3, 4, 5, and 6. In forming the ring structure, the pi bond breaks in such a way that the 2 electrons from this bond goes to oxygen and it becomes negatively charged, while the carbon becomes positively charged. Carbon atom number 2 and carbon atom and not carbon atom number 1. So also in carbon atom number 5, the bond between oxygen and hydrogen breaks in such way that oxygen becomes negatively charged while hydrogen becomes positively charged. The positively charged hydrogen atom from carbon atom number 5 is attracted by the negatively charged oxygen atom in carbon atom number 2, forming the OH. The positively charged carbon atom number 2 forms bond with the negatively charged oxygen atom of carbon number 5. So the resulting ring is the 5-membered ring called Furanose ring. So the first member, second, third, fourth member, and fifth member of the ring. carbon atom number 1 and carbon atom number 6 are not the part of the ring. So they are not the part of the ring, because this is carbon atom number 1, now carbon atom number 2, number 3, number 4, number 5, and this is the last carbon atom. The carbon hydroxyl group in the carbon atom number 3 is projected into the ring. As you can appreciate, it is the only hydroxyl group which is projected to this side in the open structure. The only difference between alpha fructose and beta fructose is the orientation of the carbon atom number 1. If the carbon atom number 1 is projected downwards, then this is known as the alpha fructose. If it is projected outward, it is known as beta fructose. So this is the end of our discussion. The last session we shall discuss about how the monosaccharides combine to form disaccharides and the properties of disaccharides and the examples of disaccharides. So in the next session, we shall discuss on how the monosaccharides combine to form disaccharides, properties of disaccharides, and examples of disaccharides. I request you to share, comment, and subscribe to our YouTube channels, Machibia Online. Thank you.